Hello friends. In this video, let's look at this interesting problem. So we are given that there is a sphere, smooth sphere of radius r with a particle on top of it at the initial rest position. So initially there is a particle right on top of the sphere and the sphere is smooth, so there is no friction between the two. And then we are told that an acceleration of value a naught, which is the constant value, is imparted to the sphere. So something is being done because of which the sphere starts to accelerate, let's say in this direction, with the uniform value a naught. So as we can imagine, as the sphere moves in this direction, it's not rolling, it's drifting off sort of, but with this acceleration. How, we don't care, but it's happening. So we can imagine that this particle will start to slide off on this surface. And at some point, it will break off from the surface of the sphere. So what we need to find is that at the break-off point, what is the speed of the particle with respect to the sphere? The break-off speed of the particle with respect to the sphere is what we need to find. So let's work this out. So since we need to find the speed with respect to the sphere, let's set our frame of reference as the sphere. So frame of reference is sphere, which is accelerating. So we are told that the sphere is accelerating at value a naught. So we'll need to keep that into account when we are accounting for forces acting on the particle. So let's look at that. Let's say, so I drew a circle here, but let's imagine a little bit. From the frame of reference of the sphere, the particle is moving in a circular motion with the center as the center of the sphere. Initially, the particle is at the top, and at some point before the break-off, up until the break-off, the motion is circular. So at some point before the break-off, let's say the angle traversed by that circular motion is theta. Frame of reference again is the sphere. So if the particle is here, so what are the forces acting on this particle in this frame of reference? So of course there is gravity, so the weight of the particle. Let's assume the mass of the particle is m, so mg is the weight. Because the sphere, the frame of reference itself is accelerating with value a naught in, let's say, the right direction, so there is a force, a pseudo force ma naught in the left direction, and then there is a normal reaction which is perpendicular to the surface of the sphere. So this will be the tangential direction of tangential speed. So now if this is theta, then this angle is theta and this angle is theta. Now we know that in this frame of reference, the particle is undergoing a circular motion whose radius is r. So what are the forces acting? So there is, towards the center, there is component of the weight, which is mg cos theta. And then away from the center, there is n and ma naught sine theta. So we can say that mg cos theta minus n minus ma naught sine theta is mv square upon r, where v is the tangential speed of the particle. Now at break-off, the contact between the particle and the sphere will stop existing. So there will be no question of a normal reaction at break-off. But right at the time of the break-off, that will be the end of the circular motion. So this equation would still hold, except that there will be no normal reaction. So at break-off instant, n equals 0. So therefore, mg cos theta, where theta is the angle of the break-off, minus ma naught sine theta will be equal to mv square over r, where v now is the break-off speed with respect to the sphere, the thing that we need to calculate. So m cancels out. So this gives us v square over r equals g cos theta minus a naught sine theta. Let's call this equation number 1. Now let's look at the work energy equation for this particle in the same frame of reference, which is the sphere. So if this is the motion, this is the center of the sphere, this is the angle theta, we have this as the radius and this as the radius r. Particle is here now. The basic concept is that the change in kinetic energy equals total work done on the particle. Now obviously initially the particle had zero speed in the reference frame of the sphere, and at the break of time the speed is v, so change in kinetic energy is nothing but half mv square. Now if we look at the total work done, we have to consider all the forces. So now the normal force is always perpendicular to the displacement of the particle at any instant. So let's say if at some instant the particle is here, then the normal force and displacement are always perpendicular. So at any instant we'll find that the dot product of the vector normal force and the displacement vector at that time will be 0. And if you integrate this, the integration of this thing will tell you the total work done. So integration of n ds over the from 0 to theta, simply because this is 0 at every instant, so total work done by the normal force will be 0. The other two forces are the weight and ma naught. So let's look at them. So let's draw the diagram again. All right. So the displacement of the particle is from this point to this point. So there is vertical displacement as well as horizontal displacement. Now the work done by the weight mg, equals mg times the displacement in the vertical direction, which is r minus this, which is r cos theta. So this is r, so this value is r cos theta, and hence this displacement is r minus r cos theta. So the work done by the weight mg is mg times the displacement, which is r minus r cos theta. So this implies that work done by the weight equals mgr 1 minus cos theta. Similarly, work done by the force ma naught is equal to ma naught times the displacement in that direction, which is this, the length of this line, which is r sine theta. So therefore, if we apply this equation, then half mv square equals work done by the weight plus work done by the force ma naught. So therefore, half mv square equals mgr 1 minus cos theta plus ma naught r sine theta. M goes away, and we bring r to the left hand side and take 2 to the right hand side. So then we get v square over r equals 2g minus 2g cos theta plus 2a naught sine theta. Let's call this equation number 2. Now equation number 1 has v square over r equals g cos theta minus a naught sine theta, and equation number 2 has v square over r equals this value. So we can equate the right hand sides of both the equations. So 1 and 2 imply that g cos theta minus a naught sine theta equals 2g minus 2g cos theta plus 2a naught sine theta. Now we take this term and this term to the left hand side. So we get 3g cos theta minus 3a naught sine theta equals 2g, and therefore g cos theta minus a naught sine theta is 2 over 3g. This is equation number 3. Now if we look at equation number 1, the right hand side of it is g cos theta minus a naught sine theta, which is equal to V square over R. So G cos theta minus A naught sin theta is the left hand side of equation 3. Hence, we can say that V square over R is equal to this value. Therefore, 1 and 3 imply that V square over R is 2 over 3 times G, and therefore V equal to square root of 2 over 3 RG, and that is our answer. Thank you.